Hi, everyone. Welcome to the online seminar on mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our distinguished speaker, Professor Mac Jordan from UC Berkeley. Professor Jordan is a Pei-Hong Chen Distinguished Professor in the Department of EECS and the Department of Statistics at UC Berkeley. His research interests bridge the computational, statistical, cognitive, and biological sciences. He has made countless contributions that lay the foundation for what we are working on today. He and his students have influenced several generations of researchers in various fields. Professor Jordan has won whatever prize could be won by a statistician or a computer scientist. He is a member or fellow of all the academies and institutions we can think of. Professor Jordan is a member of the National Academy of Science, a member of National Academy of Engineering, and a member of American Academy of Arts and Sciences. He is a fellow of the American Association for the Advancement of Science. He has been named a Neyman Lecturer and a Medallion Lecturer by the Institute of Mathematical Statistics. He was a plenary lecturer at the International Congress of International Congress of Mathematicians in 2018. Besides, he is a recipient of the IEEE John von Neumann Medal in 2020, the IGCAI Research Excellence Award in 2016, the David Rumelhart Prize in 2015, and the Alan Newell Award in 2009. He is also a fellow of the IEEE, ACM, ASA, CSS, IEEE, IMS, ISBA, and SIAM. In 2016, Professor Jordan was named the most influential computer scientist worldwide in an article published in Science. Today, Professor Jordan is going to talk about optimization with momentum, dynamical, variational, and symplectic perspectives. Please join me in welcoming him.
All right, thank you very much for that very nice introduction and welcome. Thank you for running this seminar series. I'm honored to be included among some of the really great speakers that this series has had so far and will have in the future. I'm joining you from Italy. My family is Italian and I have an Italian passport. So even in this strange era, I was able to travel and come to a country which has done a pretty good job with the pandemic and feels happy and safe, at least for now. So it's evening time here and I'm sitting in a nice chair with a cat next to me, and there may be a bit of noise because it's Italy, right? There's always some noise around. So don't mind if there's some noise, hopefully. Yeah, so this topic is near and dear to my heart. It's really about optimization and taking various perspectives on optimization coming from nearby fields, in particular from dynamical systems and physics. I'm going to name a number of people along the way who've been helping with this. It's not just me and my group, it's a lot of other people. I started to get interested in this when I took finally a sabbatical for the first time about 5 or 6 years ago. I went to Paris, and one of my ex-students there, Francis Bach, has become a real leader in French machine learning and especially connections to optimization. And then I saw a week-long lecture series by Yuri Nestorov, and that really inspired me to think more about this topic. So today's lecture is going to be very mathematical. We're going to try to ask and even maybe answer some fundamental questions about things like how fast can you go downhill? What's the fastest you can possibly go? And is there a kind of energy principle for saying how fast you can go? And we're going to find that it's really important to be not just in discrete time, which is where most of the research and optimization has been, and computer science for that matter. We're very, very focused on discrete time. But we're really going to need the topological help that comes from being in continuous time. And then we're going to find that interesting phenomena only can be perceived in continuous time. And moreover, then you have to worry about how to discretize and still preserve the phenomena you discovered in continuous time. So that kind of gives you a flavor of why there's all these buzzwords in my title. Variational is going to have to do with trying to say something about the best you can do. Hamiltonian brings in dynamics, and symplectic has to do with discretization. Okay, so let's see if I can move along here. All right, so I'm going to jump in pretty quickly, but just let me say a couple of words. This is sort of a 10-year-old slide, but it reflects the fact that for much of my career, I've thought of myself both as a statistician and a computer scientist, and I've been interested in quantitative trade-offs between these fields. How long does it take to come up with an inference and have a guarantee on that inference? A real notion of a confidence interval, and how long does it take to form a confidence interval? And when I say long, I mean both in terms of amount of data, but also real time. Many data analysis problems have a time budget, especially like right now in the coronavirus era. You can't wait for a year or two to make a decision. You need to make a decision quickly. And that's going to be increasingly true as we see technological artifacts more and more in our lives working with us in real time, not just after having gathered a large data set. All right, so if we're going to start talking about computation together with inference, we have to have a computational model and an inferential model. For me, the inferential model is given to us really by classical statistics. Both Bayesian and frequentist, to me, continue to be the framework on which I understand inference. But computation is more up for grabs. It's a newer field. Statistics is 300 years old. Computer science, maybe 100. And it's still kind of exploring what should be the computational model for various kinds of problems. And for these problems of inference, where it's not important to get the exact result, and it's important to get results quickly, and also to worry about uncertainty, new computational models seem to be needed. And so optimization has really stepped up to provide that computational model. It provides algorithms, but also insight, and even provides lower bounds. It also connects to sampling ideas and allowing us to talk about a kind of a blend of optimization and sampling. All right, so when I was a student many years ago, and also a young faculty member, I learned some optimization, but it was presented as a dead field. It was kind of done. It had solved all the problems. There was the simplex algorithm, there was conjugate gradient, there were rates known, there was good software, and there was just not much left to do. And that's completely changed. It's now a very lively field, many new open problems. And a lot of them have to come to, by tackling problems at scale, in particular coming from statistics, machine learning, or whatever. So with millions of variables, millions of terms, sampling, non-convexity, uncertainties, parallel distributed architectures, brand new problems have emerged. And many of these are theoretical problems, and many of them are fundamental problems involving trade-offs. So we're having to do more mathematics than I think that we ever thought we had to do. So while much of the machine learning field has become much more empirical and providing demonstrations of various capabilities, which is perfectly fine, I personally have found it's been much more exciting to me and important to kind of head off in a more mathematical direction. All right, so if we have these new kind of constraints, millions of variables, millions of terms, and so on and so forth, what kind of machinery are we going to be talking about? What kind of algorithms? What kind of machines? What kind of computational model? And there's some agreement that right now, at least, it's been very useful to focus on a few very simple ingredients. We're going to work with gradient methods. We're not going to tend to work on higher order methods as much as in the past of optimization. So Hessians are used very sparingly. It's because we don't have enough time to calculate a full Hessian, or even enough statistical power to calculate it accurately. Moreover, even a gradient itself might take a long time to compute, because you have to sum over all the data. So stochastic methods have dominated. And then finally, acceleration has turned out to be very, very important, partly because it's algorithmically helpful to accelerate, but more because it gives you ideas of lower bounds. What's the best you can do? Are you done with the problem? Can you reformulate the problem to do something to get some extra power? Okay, so if you now bring statistics and computation together, you want to take the lower bounds from the two fields and bring them together. Optimization provides lower bounds. Statistics provides lower bounds, something like the Kramer-Rao lower bound and so on. There's many others. And these are two fields that have fairly mature lower bound technology and upper bounds. And so you can start to not just bring them together in one field, you can have them cross across the fields. So that's where we're kind of heading. Okay, so this says part 2 here. That's a typo. This should be part 1. I'm going to start with a paper that's about 3 years old now. This was done with my students, Andre Whipperson and Aisha Wilson. Both made major contributions here. Their thesis was about this topic. We also had some help from Michael Betancourt on symplectic ideas at some point. And this really is trying to ask an interesting question, which is, what is the optimal way to optimize? Okay, so that's, I think, a fantastically interesting question. Optimization procedures certainly optimize, they arrive at the bottom of something, but is there a best way to optimize? Is there a fastest way to get down the hill for different kinds of hills and do it under, you know, a broad set of conditions? So that's kind of a way of thinking I associate with someone like a Yuri Nesterov or in particular Nemirovsky. Really the Russian school has thought in these terms. So we're going to bring that way of thinking about what's the best way to optimize, and we're going to bring it into continuous time, because in continuous time, you can really start to strip away some of the algebra really and isolate some principles. All right, so let me just kind of make a kind of grand statement about optimization. It's a little bit of a caricature. But if I think about fields that are really mature mathematically, they tend to both use differentiation and integration. So differentiation and integration, of course, are linked by fundamental theorem of calculus. And mature fields really use both sides of that theorem. So physics certainly has, you know, differential equations, lots of differentiation, F equals ma, you know, Maxwell's equations, and so on. But there's also Lagrangian and Hamiltonian perspectives that rewrite those equations and express them in terms of integrals or integral equations. And the interplay between the integration and differentiation really defines a large number of areas of physics. Statistics has lots of integrals, certainly in the Bayesian field, but not only, and Laplace expansions and saddle point expansions and so on, but also has lots of derivatives, you know, M estimators and maximum likelihood are based on derivatives. The numerical disciplines, finite element analysis, is a variational field that also has lots of partial differential equations. Monte Carlo blends these two sides of the coin as well. So I could go on, but those are some of the disciplines that I've learned enough about to kind of appreciate the interplay between these ways of thinking. And optimization, I would argue, does not have such a strong interplay. So it's really mostly differentiation. If you pick up a book on optimization, you'll see lots of derivatives and Hessians and gradients and so on, and you'll very rarely see an integral sign. And if you do, it's probably just in a Taylor expansion and it's trying to tell you, you know, about a remainder. Okay, so I think that that's really an opportunity, that there is probably something missing in optimization that brings a variational perspective to bear in thinking about how to optimize, especially if you're trying to think about what's a notion of an optimal way to optimize. Is there some kind of an energy principle that's expressed and perhaps as an integral of some kind? All right, so let's start with unconstrained convex optimization, just to get really clear on ideas here. And I have to tell some people to be quiet here. It's late here and people are finishing dinner. Let's minimize a convex function. Let's make it be a smooth function, like a Euclidean, just for simplicity. I've written down gradient descent here. We take the gradient and we make a step of size beta. And this course algorithm is 150 years old. More recently, it's now understood how to think about a convergence rate for an algorithm like this. So if this is a convex problem and it's smooth, then we know that this algorithm converges at rate 1 over k. Not a hard thing to prove. All right, before I move on to this, so at some point, Nemirovsky, Yudin wrote a textbook, and we're thinking about is something of the form, is this the best you can do for this class of problems? Is there a lower bound on the rate? And what would that mean? Well, that's a complexity theory question, right? And so to talk about complexity theory, you have to have a machine in mind. And so if you thought about this in the context of, say, a Turing machine, you'd be sort of stuck, because Turing machine can do everything, and it might just look at the description of the function and hop to the answer. Nemirovsky had a better idea, which was, let's define a gradient-based machine. It's allowed to look at the current gradient and all previous gradients. It can store in a memory, and it has to take a step within the linear span of all the gradients it's seen so far. So that includes conjugate gradient and gradient descent, and you know, it's a powerful machine, but it's not everything. It's not Turing complete. Okay, now in that machine, he was able to prove that there is a lower bound of 1 over k squared. Okay, so in principle, you should be able to go faster than 1 over k. And in some ways, that's a surprise, because gradient descent is steepest descent. It's taking if you could only look at gradients, it gives you the steepest direction down the hill. And it could have been that this was just a bad bound. It was too low, and a better bound could have been found, or it could have been there was a better algorithm. And it turned out there was a better algorithm. So this was discovered by Yuri Nesterov in 1983. And here is Nesterov's famous acceleration algorithm written in a particular way. It's not just one equation, it's two equations. So we have a second variable here, which we're calling y. Y is updated more or less as the gradient using the x variable. And then x is updated as really a rotation, if you will. Think of that lambda as like a cosine or sine. So it's a rotation of the last two values of y. So this has a flavor of momentum. It's using sort of two gradients, if you will. And, you know, but it's just an algorithm. And why, you know, why is it any better than anything else? Nesterov was able to prove that this thing obtains the optimal convergence rate, the lower bound of 1 over k squared. So there's a whole technology developed to do this called estimating equations. It's somewhat complex. It's very algebraic. It's partly because it's being done in discrete time. But anyway, after this was done in '83, there's now been accelerated methods developed for many, many other kinds of problems, non-Euclidean and constrained and so on and so forth. All right, so you have gradient methods and you have accelerated methods. Just a couple of remarks about accelerated methods. I think many people now know about them because they've appeared in many, many fields. They have many, many names. These are not descent methods. They will go down and they will go up again. And that, first of all, seems a bit surprising. If you're trying to get down the hill as quickly as possible, why should you ever go up again? And that's one of the things we're going to be talking about. Okay, so we're going to argue that the way to understand these things, at least to get new insights into this kind of class of algorithms, is to go into continuous time. So let's do this first of all with gradient flow. So you know, gradient flow is a differential equation. X dot is equal to minus the gradient. And discrete, if you discretize this with, say, the Euler method, you get gradient descent. Gradient flow doesn't have a step size. That's nice. So it's a little easier to analyze. And you can analyze this. You can even write down the Lyapunov function. You can get a rate for this. If you have a convex function f that's just smooth, then this has a rate of 1 over t, which corresponds to the 1 over k you get in discrete time. And there's, you know, huge amounts of analysis of this, including topological results of all sorts in mathematics. Now you can take the Nesterov, those two equations that I showed on the previous slide, and ask what happens if I take the step size to 0. Obviously, you'll get out a differential equation. You could take the step size to 0 in different ways, and there's been now a lot of work on different ways of doing that. I've been working on that with colleagues Ben Shi and Wei-Jie Su. And you get out different ODEs, but the simplest way of doing this is just to take the step size to 0 in a straightforward way. You get out the following ODE. It's second order, obviously, because you had two equations. It has some damping there, 1 over t, and it's got a mysterious 3 up there. That's kind of surprising. And there it is. It's a little second order differential equation. It will oscillate. And you can analyze the oscillations with Bessel functions and so on and get some insights into this particular differential equation. So we found that really, you know, very interesting and provocative. And, you know, but it left us a little short, right? So why this differential equation? Why that 3? Why is this a good differential equation? Is there some principle that gave you this differential equation and will give you different differential equations and other problems? And can we figure out what such a principle might be? All right, so this is a little bit, again, somewhat grandiose, but it's a little bit like Lagrange looking at f equals ma and saying, well, that's a perfectly nice equation, but where does it come from? Is there an underlying principle, a Lagrangian of some kind, that derives that equation? All right, so that's what with Aisha and Andre we started working on, and we came up with such a principle. And so on just one slide here, I'm going to try to convey what that idea is. We were able to find a Bregman Lagrangian, a time-varying Lagrangian in continuous time that captures many, many accelerated algorithms expressed in continuous time. So it has a bunch of, it's time-varying, and it has a bunch of alpha, beta, and gamma functions there of time. Those are not the important part. Those are just degrees of freedom that give us a space of algorithms and not just one algorithm. They're just diffeomorphisms. The important part is that Bregman divergence there, d sub h. Bregman divergences depend on an auxiliary function h that kind of measures distance in different ways. And so we're measuring Bregman divergence between x and x plus a time-shifted x dot. So it's kind of a stretching or elasticity in the direction of motion, measured in a particular way. And then we subtract off f of x, again, time-scaled. Now, if h is set to a quadratic function, then that Bregman divergence just reduces to 1/2 x dot squared. So it's a kinetic energy. And so this is literally a Lagrangian. It's a kinetic energy minus a scaled potential energy. Okay, so there's your Bregman divergence, which generates a Lagrangian. What do you do with Lagrangians? Well, you do calculus of variations. You put them inside of an integral. That gives you a number, often called the action. Then you minimize that over paths. So maybe on that black path there, this integral is minimized. And so that's the solution to the problem. And you can find these solutions by writing down the Euler-Lagrange equations, kind of something like setting all the partial derivatives to 0. And if you set all those, if you use the Euler-Lagrange equations and apply it to the Lagrange at the top of the page, it's like a 2-line derivation. You will get out a master differential equation, which is at the bottom of the page here. It is a second order equation, x double dot. It's got a damping term there involving the alphas, not the betas and gammas, just the alphas. And then it's got a big term, which is really just a bunch of geometry. Depends on that h function, and some scaling. Okay, so why is this an interesting differential equation? Well, first of all, it contains lots of well-known accelerated algorithms. In particular, the Su-Boyd-Candice algorithm is in there. If you set alpha of t equal to logarithm of t, and you set beta t in a particular way, which we call it ideal scaling law, then you will get out the 3 over t, and so you'll get, and if you set the h to quadratic, that whole third term there will just will simplify, cancel. And then there's many other accelerated algorithms, including mirror descent and accelerated mirror descent and so on in this equation. So it's kind of a master equation, but it has a lot more interesting properties than just that. First of all, you can write down a convergence rate for this equation once and for all. And so this is Aisha Wilson's work. She was able to find a Lyapunov function that really just involves the beta. It's exponential in the beta. And so once you've picked the beta, that gives you the rate for the convergence of this differential equation. And it's just a simple Lyapunov argument. You get a convergence rate once and for all these classes of methods. There is the Lyapunov function right there. As I alluded to, it's just exponential in beta. And the proof of that this is the convergence rate is just to take a derivative of this Lyapunov function that I've written down in the proof there. Okay, and so Aisha has a long paper on this if you want to hear more about this. Now let me go back to this previous slide, because now I want to start to get to the geometry of this. Okay, so the oddity, now that we've gone into continuous time, is that we've somehow lost the lower bound. At least it seems like we've lost the lower bound, because I can ask to go at a certain rate by setting alpha and beta. So suppose I set alpha to 1 over t, I know I will get gradient flow, and that differential equation there will just reduce to gradient flow, and I will get a rate of 1 over t, which is what gradient flow does. If I choose alpha to be 2 logarithm t, I will get out the Su-Boyd and Candice algorithm, and it will have a rate of 1 over t squared. All right, so is that the end of the story? Well, no, I can set alpha of t to many different ways. If I set alpha of t just equal to t, then I plug this in, I'll get a different differential equation, and it will actually converge at an exponential rate. Okay, so e to the minus beta t, beta is now t, so I get an exponential rate. So that seems strange, because we know we can't get exponential rates. That's the lower bound of Nemirovsky and Newton. But that's in discrete time. In continuous time, we can get any rate we want. Why? Well, because I can just do a change of variables. I can change my clock. Instead of using one clock, I just do a diffeomorphism. I use a different clock, and I can go at any rate I want. So has the phenomenon really vanished? Well, no, it hasn't, because here's the interesting thing. This Lagrangian has an invariance property. It's equivariant, meaning that no matter which differential equations I use in this family, they'll all follow the same path in the phase space. And now they'll follow that path at different rates. Some of them will go slowly, some will go faster, but they all follow the same path. All right, so the notion of being a best algorithm as captured by this Lagrangian has to do with the geometry of the path, and you have to slow down around the curves, and you can go faster when the path is straightened out. And so that's what this Lagrangian has captured. It's not about the speed, it's about the path, okay? So that's a little simple proof, again, that is true. And now we're going to be exploiting that as we go forward. Okay. All right, so this slide was written a couple of years ago. This was kind of the mysteries, which is that, okay, in continuous time, you go as fast as you want. The geometry sort of influences what path you take. That's interesting. But now we got to get back to discrete time to actually get an algorithm. And we can't go as fast as we want. So there must be a phase transit, a breaking point where we can no longer discretize the dynamics. So what happens when we reach that clock speed where we can discretize? And then once we can discretize and still preserve our fast rate, how do we do that? Okay, so I was giving a talk somewhere, I think it was in Los Angeles, and showed that slide about the mysteries, and I clicked in my mind that a class I'd taken back when I was a young professor at MIT on differential equations, and at the end of it, it had a little section on symplectic integration. And I remember that symplectic integration was sort of a way to be able to integrate such that you could go much faster. And you can somehow go as fast as you possibly, you could cancel certain higher order terms and go very, very fast. And so I thought that must be somehow related here. All right, so let me just say it is related. So that's kind of be the rest of the talk. So let me say a little about what symplectic integration is, if you don't know already. So this is a topic that goes back, over 100 years, developed by people like Jacobi, Hamilton, Poincaré, and others. And they were interested in discretizing differential equations. Not entirely clear why, because it was before there were computers, but clearly they had lots of differential equations in their lives. They had Maxwell's equations, they had Newtonian mechanics, and so on and so forth. And they had to, I guess, solve these things numerically, so they needed to discretize it, even though to do it on paper. In any case, they wanted to discretize them in a particular way. They wanted to discretize it such that you still conserved certain relevant quantities from physics, like momentum or energy. So if you're approximately solving a differential equation, you're hopping along a set of points that are near the true flow. You might now ask about what's happening to the energy or the momentum, which the physics tells me must be conserved exactly. Well, if you just do this approximation in some arbitrary way, you'll be approximately conserving the physics, the physical quantities, and that's not good. You'd like to exactly conserve it. So they ask the question, can you exactly conserve these quantities as you flow along, approximately along a continuous path? And is that possible? And the answer is yes. And so the way to think about this is that you think about a vector field a little differently. Classically, a dynamical system is just a vector field. I arrive at a point in space, I have a vector leaving that point, and I follow it for a little distance, integrate a little bit, and then I hop to the point and I repeat. They thought about it differently. They thought about what happens if I have a triple of vectors at a point in the space. As that triple moves along, it's going to shear. If it flows along the flow lines, it'll shear, and its volume element will change in general. Its its volume of that little triple will change. I could ask that as it shears, that its volume stays constant. And in doing so, volume is a determinant. Determinant is a polynomial. I'm just putting a polynomial constraint on my discretization. All right. And maybe I have enough degrees of freedom that I can put that constraint on there and exactly respect it. And the answer is that yes, you can. And they developed particular methods that allow you to do that. All right. Now, when they developed those, it turned out that these had important numerical properties. It's sort of taken 100 years after that to really unpack all those numerical properties. All right. So I'll be talking about that in the rest of the talk. But just let me say a little bit of how you do this. And I'm going to kind of go quickly here, but just to say it's entirely standard. So instead of working with Lagrangians, it's convenient to change to Hamiltonians. You just do a Legendre transform, introduce a momentum variable. And now that we're in the Hamiltonian world instead of Lagrangian world, there is a standard set of symplectic integrators and things like leapfrog, if you've heard of that as an example. And often these are interlacings of an implicit method and an explicit method. The explicit method is usually computationally straightforward. The implicit is not, but there's ways of doing the implicit to make it also computationally tractable. And huge literatures on this. So we did that for our Bregman Lagrangian. So we converted, first of all, the Bregman Lagrangian to a Bregman Hamiltonian. Then we wrote down a symplectic integrator for that, and then we put that on the computer and integrate. So this is a particular high-dimensional quadratic, and this is the function value as we go over time, and you can see it's kind of oscillating and going down at a well-defined rate. If you compare this to Nesterov, here is Nesterov and against the symplectic integrator on a different problem, so there's kind of a more of a speed up near the end. It looks like it's about just as good as Nesterov. And in fact, it's actually better than Nesterov. If you turn up the step size, everything's going to shift over to the left here. Oops, everything is going to shift over to the left. And you can see that symplectic continues to converge, but Nesterov goes unstable. All right, so symplectic is allowing you to take a bigger step size and still converge. So you're able to go faster with symplectic than Nesterov. Okay, so the last part of the talk is recent work of this past 6 months with Guy Franca and René Vidal, who've been at Johns Hopkins. Guy has now joined me in Berkeley. And we've been trying to take this symplectic idea seriously and try to understand when can you integrate symplectically and prove that you maintain these fast convergence rates from continuous time in discrete time. Okay, so in doing this line of work, we had to face the kind of the conundrum which symplectic ideas have classically been based on Hamiltonians, and Hamiltonians are for conserved systems, at least classically, and conserved systems are ones which oscillate. So perfectly fine for lots of problems in physics, but we're not trying to oscillate, we're trying to go downhill, and so we're trying to not clearly oscillate, we want to converge to a point. So the setup somehow just doesn't match very well with the goals of doing dynamical systems for optimization. Now, of course, physics is vast and mathematics is vast. There surely is dissipative ideas in symplectic world, and in fact there is, and that's what we're now going to be bringing out and bringing into contact with gradient-based optimization. Okay, so there's a paper we have on this, and I'm going to refer you to the paper to go slowly through this. I'm going to try to give some of the basic concepts. If you have differential geometry or Hamiltonian background, this will be, I think, fairly straightforward. If you don't, you know, hopefully you'll get the main concepts here and you'll be motivated to have a look at the paper. And I'm just going to try to give, you know, let the mathematics kind of serve as kind of the pictorial background here and try to kind of convey the conceptual ideas. All right, so first of all, just a little bit of the kind of the physics setting here, you know, that Hamilton and others were trying to get at. So we're going to be talking about position variables and momentum variables, very natural because we're in this world where we have this momentum building up. And that kind of also, when I alluded to these methods not being descent methods earlier, they are momentum methods. So they like to go downhill, but they'll come back up again so they can build up more momentum, and that allows them to go faster. So from a physics point of view, it makes a lot of sense. So we have explicit momentum variables P and position variables Q. The Hamiltonian perspective is to write down an overall functional, take derivative, partial derivatives, and let that define your dynamics. Our Hamiltonian will be time varying instead of the usual time invariant. Okay, so we're going to be on a smooth manifold, so we can do pretty general problems, and our pair Q and P will lie in the so-called cotangent bundle. So this is just differential geometry language. Okay, so now we want to set up a Hamiltonian which can be viewed as solving an optimization problem. We're optimizing with this function f. All right, and so our goal is going to be able to do this in continuous time where we get all these really great insights and bring them back to discrete time and then look at the interplay between discrete and continuous. Okay, so what do we want? We want to dissipate, so we have to have this explicitly time-varying Hamiltonian, and can we relate dissipative Hamiltonians to optimization algorithms? Okay, all right, now why do you work in the Hamiltonian world where there's this notion of invariance, and invariance was classically the motivation for studying Hamiltonian ideas. It was, you know, that you capture the notion of physical laws, you know, invariances, conservation laws. But we don't necessarily have a conservation law here or an obvious one. We don't necessarily want to conserve things. We want to dissipate. Okay. So we're going to be able to still use symplectic geometry ideas, and we're going to do that by embedding our problem in a bigger problem. That embedding is going to be called symplectification, and use symplectic ideas up in the bigger space. And then we're going to do something called a gauge fixing, which brings us back down to the the original space in a way that provably conserves the quantities or conserves the rates we want to conserve. All right, now we seem to be now not so clearly why are we motivated to look at invariances. All right, it seems to have been kind of gone. All right, well, it's because invariances relate to the error analysis. So to get this conservation of the rate, that we get the fast rates when we discretize, we want to be able to do backward error analysis. And so when you do differential equation discretization, you don't just write down a Taylor expansion of some kind. You have to prove something about certain error terms being under control, and that's called backward error analysis. And backward error analysis relates very, very cleanly, neatly, and deeply to Hamiltonian symplectic ideas. Okay, so backward error analysis here, the way to think about it is that there's an exact flow, phi sub t here, and we're going to write down an approximate numerical map, phi sub h, which has a step size, and it's going to be approximating the exact flow phi sub t. And we want to do that up to some order, h to some power r to the plus 1. And the way to think about this is that the numerical method phi sub h can be thought of as the exact flow of a perturbed dynamical system. And we can write down a Hamiltonian for that perturbed system, okay? And now we can, work with all our tools in continuous time and still read off the kind of accuracies that we're getting when we discretize, okay? So this is due to lots of very famous applied mathematicians. There's some names down there, and there are textbooks on this material. Okay, so you can take the perturbed vector field now and you can truncate it to get yourself a system which is the approximate system. And the mathematics tells you that you can do this in a controlled way, so that you can have your approximate flow x tilde close to your true flow, uniformly so, with control over the errors, e to the minus r, where r is this order of the error. Okay, so all right, so we are going to be exploiting this by still maintaining some of the invariances that symplectic ideas give us, while leaving behind the conservation of energy one, which we don't need. Okay, so just a little bit more language. So we have these symplectic manifolds and Hamiltonian systems. What's a symplectic manifold? Well, a symplectic manifold is just one where there's a particular kind of volume element, if you will, a symplectic two form, okay? So this is kind of the generalization of the determinant. It is a quantity that you'd like to conserve, and a manifold of even dimension has these symplectic two forms, okay? So this is, if again you're not been exposed to this before, this will be somewhat mysterious, but just think about this as kind of like conserving a quantity like momentum or energy or other kind of first integrals of differential equations. The general differential geometry language for this is a two form, and symplectic two forms are these kind of symmetric exterior forms. Okay. All right, so now there's a theorem which kind of underlies all this, which is a dynamical system with a certain phase space preserves the symplectic structure if and only if it is a conservative Hamiltonian system. Okay, so Hamiltonian systems are not only useful to talk about dynamics, they are critical. You have to have them if you're going to talk about these ideas of these symplectic structures being conserved, and therefore, as I'm going to talk about in a minute, connections to backward error analysis. Okay, so preserving here just again has a differential geometry language behind it. It means a certain so-called Lie derivative. When it applies to the vector field, the Lie derivative is equal to 0. Okay. All right. So it is possible to construct these symplectic integrators now in a very systematic way. If you want to preserve a two-form omega, you're going to throw together a couple of these approximate flows, phi sub h and its conjugate, before and after. So this is kind of the interlacing I was referring to. This kind of has an anti-symmetric property now, so that you'll still conserve omega if phi is set up in this particular way. Okay, so because the Lie derivative is 0, that means that the structure has been preserved. H and x tilde have the same structure. The truncated vector field and the original vector field have the same structure. Okay. All right, so now we can put that together with the idea of backward error analysis. All right, so you can now assume that you have any kind of a Lipschitz function of your flow. You can take your continuous flow, phi sub TL, and you can discretize and get a bound on the error. Okay, so basically, because you're preserving the symplectic form exactly, and you've just had a little perturbation off of that, your Hamiltonian is preserved a lot, you can do an expansion and get control over your error. Okay, so that argument's very classical. It took about 100 years to build up, but it lies behind huge, vast parts of applied mathematics. If you're integrating, say, the dynamics behind a protein or the cosmos or the climate, these are extremely complicated dynamical systems. You would mostly use the symplectic integrators for these things. Symplectic integrators allow you, by having this bounded error, to have a much larger step size and still have control over the error. Okay, so now the problem is that we're going to go into a world where we've broken that by having a time-varying Hamiltonian, and some of the mathematics I just alluded to is now gone. Right? Right. So what we're going to do is kind of a very natural move. We're going to embed ourselves in a manifold of one higher dimension. So we're going to call that a pre-symplectic manifold. And the general definition allows you to go up to even higher dimensions. We're only going to need one more. And so we embed the symplectic manifold into this higher dimension, which is a symplectic manifold, as one more dimension. Okay. All right. So roughly what we're doing here is that we're kind of reifying our original time variable, and we're giving ourselves an energy that's associated with that, with a new time variable, and we're making those to be conjugate pairs. Okay. So the energy is now allowed to decrease because it's going to kind of be trading off against this new time variable, which is going to allow us still to conserve on the bigger symplectic manifold the a symplectic form on that bigger manifold. All right, so here's kind of a picture that we took our complicated dynamics living on T star M bar, and we embedded this in a bigger manifold T star M hat, in which we do all the usual symplectic geometry and dynamical system stuff. And now all you have to do is to worry about how to get from the bigger manifold down to the smaller manifold, and that's called gauge fixing. And there is a particular way to kind of get rid of the extra degrees of freedom here. You know, for details, see the paper, but it's kind of a standard gauge fixing where I've written it up there. Okay, so we now have kind of all the machinery working in the bigger space. The gauge fixing is done in a way to preserve that structure, the relevant parts of that structure for our convergence rates. And we can now define a notion of a pre-symplectic integrator. So it just needs to be a reduction under this gauge fixing of a symplectic integrator for the symplectification, the bigger manifold. All right, so having set all that up, and now it's straightforward to show that we still have this backward error property, that we can control our error going from the continuous dynamical system to the numerical or discrete dynamical system, because we've done it in the symplectification, and we've preserved that the symplectic, the relevant parts of the symplectic structure as we go to the embedded manifold. All right. So now we can start looking at particular Hamiltonians which are relevant to optimization. And so the ones that I showed you earlier were of the form of a kinetic energy and a potential energy that were time scaled. Here's a Hamiltonian version of that where we don't subtract, we add the F. So this is a pretty general form, includes the Bregman Hamiltonian. And we now have a theorem for this, which is that if we use a pre-symplectic integrator for that Hamiltonian, it will be a rate matching discretization, i.e. our continuous rate and our discrete rate will be the same up to a very, very small error. Okay, so that's a theorem we've been looking for 2 or 3 years. That was kind of one of the mysteries I referred to earlier, and we now have such a theorem. Okay, so we can get rate matching discretization. The error is actually extremely small here, and it really is there's no need to have higher order integrators. R can only be 1, and that's plenty good enough for the optimization kind of problems. The other part, which is important, which I don't want to get into details here, but there's a way to see how this perspective distinguishes the heavy ball damping from the Nesterov damping, which is a particular choice of the functional in this gauge. Okay, here is explicitly the Bregman-Hamiltonian, which we started the talk with. It again is the Hamiltonian version of the Bregman-Lagrangian I showed you earlier. And if you just now do Hamilton's equations to that Bregman-Hamiltonian, you get out that master differential equation there, which is the same one I showed you earlier. All right. And I showed you with a Lyapunov argument before a convergence rate in continuous time. And we now have the machinery to say that we can guarantee you'll get exactly that same rate when you go over to discrete time. Here is actually the actual example of the leapfrog method. This is done for the simple case of the Bregman divergence being just quadratic. And there is an explicit symplectic leapfrog integrator. It's an interlacing of full step sizes and half step sizes. And if you know this literature, you'll recognize this kind of integrator. So this you just put on the computer and it will have the guaranteed rate. And here, for kind of full generality, is an example of even a more general form of Bregman-Hamiltonian where you don't have this separable structure. And in this case, you can write down what's called a string composition. And, for a certain, I guess R is equal to 2 here, and you get simply some explicit numerical maps, which you can put into the computer and use to integrate. Okay. All right, so that's what I wanted to say about that. I'm going to take a couple more minutes to say something that's more like a little bit more like dessert. That was the meat and potatoes. But just to again summarize, we've introduced the idea of pre-symplectic integrators. We've embedded ourselves in a higher space. We're able to use the mathematics of conservative systems, even though we're looking at dissipative systems. And this allows us to talk about rate matching. A couple of other comments about this area. First of all, this kind of is on the upper bound side of things. It allows you to get actual methods that have certain rates, and we're talking about upper bounds of these rates. What about lower bound story? Because the Nemirovsky-Yudin work was lower bound stories in discrete time, and it was done with particular constructions of particular hard functions in discrete time. Well, it turns out that you can actually also get lower bounds in continuous time. And I alluded to earlier, what I alluded to earlier sounds like that's not possible because you can go as fast as you want. But again, there is a particular kind of canonical gauge fixing you can impose, and you can still read out meaningful lower bounds in continuous time if you do this. So I have a paper with Michael Muhlebach, published this year, which is on continuous time, lower bounds in continuous time. All right. The last little thing I want to do is a little bit of dessert, which is to talk about saddle point, convergence to saddle points. In particular, this little example is going to be with Nash equilibria. One could consider other kind of saddle points, but game theoretic dynamics. And I just want to mention this because here's symplectic ideas actually also come up. And here it's useful to actually not exploit this symplectic component, but to get rid of it. So to give you a little more intuition about what symplectic methods are and what they are not, this is a nice little exercise. So Eric Mazundor's a student worked with me on this at Berkeley. Just briefly, let's just talk about, simple game theoretic setting. We have a zero-sum game. So we're trying to minimize, one agent's trying to minimize a function f of x1, x2. The other agent's trying to maximize that same function with the other argument. We can write down a gradient, omega, and we can write down a Jacobian. And we'd like to find saddle points of this thing. So there's special saddle points. A Nash equilibrium are saddle points that are axis parallel. One agent wants to go up, the other agent wants to go down, and we'd like to converge to those kind of saddle points. And as many of you will know, there's been a lot of work on simultaneous gradient methods where you go ascent in one direction, descent in the other. Simple versions of this are known to fail. They can actually not even converge to limit cycles. And moreover, they can even converge to non-Nash saddle points. Meaning a saddle point which is not axis parallel, but it's been tilted. So this is not game theoretically meaningful. You don't want to converge to those things, but gradient methods will converge to those things, and that's a problem. So there's been a number of different proposals, gradient play, symplectic gradient adjustment, consensus optimization, which try to avoid some of these problems. What they do is people have been able to find ways to get them to not oscillate and actually converge. Over there on the left, you see a picture of 3 Nash equilibria. Those are the green crosses. And a blue star in the middle is a saddle point, which is a tilted saddle point. It's not a Nash equilibrium. And so, unfortunately, even though these methods are converging, that's good. They are also converging to the non-Nash equilibrium, which is bad. So what Eric has proposed a new algorithm, which we called local symplectic surgery. I've written out the algorithm there. It's using omega, and it's also using the Jacobian. And what's happening here is that this algorithm is actually canceling the symplectic component. The symplectic component here is actually what's making this algorithm converge to the tilted equilibrium. Okay, so if you cancel that, this algorithm will actually provably not converge to the non-Nash equilibrium. So you can see that on the picture there on the right. This algorithm is that dashed red line. You can see it's converging to the green star in the middle, but as soon as it gets close enough in a neighborhood, it sniffs out that it's a tilted equilibrium and moves away from that and moves over to a Nash equilibrium in the lower left-hand corner. I'm also very actively working on this with some other people. Someone named, a colleague of mine named Luca Citti in the UK. We have a new algorithm which doesn't need a Jacobian. So that's kind of been an open problem, and we've made progress on that recently. I'm going to skip that slide, and I think I should have been a conclusion slide. This is an experiment I don't want to get into. I want to go ahead and finish up. So I don't have a conclusion slide, so let me just sort of say some conclusions here. So first of all, I've just kind of given you a few high points and tried to tell a story about dynamical systems and integrators and lower bounds and upper bounds and so on and so forth. You know, I've skipped over lots and lots of details, but I've also kind of not given the broad context here. At this point, this field really needs a textbook. There are, you know, several dozen, if not hundreds of people now contributing to this field. I've been amazed and pleased by how many good ideas there come out every day on arXiv, and over the last 3 or 4 years, just it used to be only the Russians, you know, Nestrov and colleagues, but now it's sort of many others who have contributed to this. And so there are results for stochastic systems, results for Langevin systems, results for other kinds of geometry. There's results for constrained systems, and so on and so forth. Upper bounds, lower bounds, and really this field has really come quite far. So as a theoretician, it's very pleasing because we're able to give meaningful upper and lower bounds. We're able to talk about robustness. We're able to talk about kind of general problems, and really start to give guarantees of the kind that a good scientist or engineer would want to give for any kind of working real-world system. All right, so I think I'm going to go ahead and finish, and hopefully I've left time for questions if there are any. Thank you very much.
Okay, thank you, Professor Jordan, for the very nice talk. And so maybe let's look at some of the questions raised in the Q&A section. The first question is regarding on the interplay between physics and optimization. So I was wondering whether there exists some principal way to connect the physics to optimization.
Yeah, so I mean, there's a lot of principles in this talk that do connect. You know, that said, what's missing here still, and we need a really smart person to help figure this out, is why this Bregman Hamiltonian or why this Bregman Lagrangian. You know, I wrote it down in a particular way. It looks kind of plausible. It has an energy term. It has kinetic and potential. You know, there is some real physics there, but it doesn't really connect directly to the optimization problem. There's kind of not a set of axioms that say, here's the quantities you should conserve in any optimization problem, or here's the symmetries that you'd like to express. And from those axioms, we derive a Lagrangian or Hamiltonian. We don't have that. I think that's perhaps possible, but we don't have that. And we don't even know what are the actual, can we write down all the symmetries of this Hamiltonian? You know, what are some, there's more mathematical structure there that we don't know about. So I guess that's kind of what you're asking about is, you know, after Lagrange, you know, another few decades went by, or 100 years, until people started to be able to resolve those kind of questions. Maybe it'll be faster here, but yeah, there's some real mathematics still to do. having to do with deeper exploration of the geometry that underlies the energy principle, and not just the geometry underlying the surface you're trying to go downhill on.
Okay, thank you. And another question is, it seems that the results you just talked about are all continuous time results. I was wondering whether you would like to further go back to the discrete time setting by doing some discretization, or you're just happy with the continuous time results.
Okay, no, that didn't come through. The second half of the talk was a theory of how to discretize the continuous systems so that you maintained, we got control over the error, so that you maintained the convergence rates in discrete time. Mm-hmm. So the last few slides, I started to write down actual integrators. Those were discrete time algorithms that you run in discrete time on the computer, and they provably have the rate that the underlying continuous time system had.
Mm-hmm. Thank you. And another question is whether similar links between physics and optimization can be made for non-convex optimization.
Oh yeah, no, definitely. So there's a lot of open problems there still, but non-convex optimization. In fact, at Princeton, you have one of my students, Chi Chen, is a real-world expert on that, and there are others. A very productive way of thinking about that is to start to go to things like second-order stationary points. So don't just try to find a place where a gradient vanishes. Try to find a place where a gradient vanishes and you have a lower bound on the eigenstructure of the Hessian, so that when you converge, you will not converge to a saddle point, but you might converge to a local optimum. And so now you have a gradient method which is kind of flowing downhill, and it just doesn't get stuck at saddle points. It kind of veers out from them, but it won't kind of go to. It's not obviously finding a global optimum, but it will find some sort of slightly non-local geometry. And you can have rates for that. You can have geometric dependence, and moreover, Jen and Praneeth Nachapali and I have a paper for accelerated methods when there are saddle points, i.e. for non-convex optimization, and using a Hamiltonian for getting those rates. So yes, absolutely, the Hamiltonian perspective. It doesn't just help you design the algorithm by taking these partial derivatives and so on. It also helps you design the analysis, because the Hamiltonian has pieces to it, and you can analyze each one of those pieces and put them back together to get your overall rate. So yeah, there's absolutely, all the kind of, there's still much to explore, but the geometry principles that says here's when you go fast and why, and here's how to capture that with an energy principle. Yeah, very much part of this overall line of research.
So there are a few more questions just popping up. So there's a question asking whether there exists an example which demonstrates that there exists a gap between the lower and upper bounds. And if yes, any speculation to which one might be loose?
The problems that I've been focusing on here in all this line of research, there is no gap.
Okay, gotcha.
When you get into more exotic problems and stochastic problems, it starts to be the case we don't know lower bounds, or there's some very recent papers trying to find them. It's very active right now, so there still are some gaps. But the beauty of this field is that there are very few gaps, and that's not true of many other fields. Computer science has these huge gaps, exponential, polynomial kind of gaps, and here there's no gaps here for the most part.
Mm-hmm. And another question is regarding the intuition of adding the dissipative term in the Hamiltonian system. So is there a reason why we added such a term to decrease the energy?
Yeah, there absolutely is. First of all, you can't just put in an arbitrary dissipation. You will ruin your convergence rate. So this was a very carefully chosen dissipative term that has a geometric side to it. Basically, when you're going around a place where you need to go, there's a lot of curvature, you need to slow down. And so the dissipation has kind of got to get you to slow down quickly in that place so that you don't overshoot. Again, Michael Muhlebach has been a postdoc on my group, and he has a very strong dynamics background. He's written some papers on this. There's a paper, I forget the title, but you'll find that on Michael's homepage or mine. It's something like momentum methods in optimization or something. And that's a little bit more of a classical kind of control theory analysis, where you do some linearization and you really start to understand, you look at various kinds of dissipation terms and you give a physical interpretation of them. They really are kind of, oscillator dissipation terms, and you relate that directly to geometry. So it's a little more kind of hands-on control theoretic analysis instead of this slightly more abstract one you've seen today. So that would be the best paper I know of right now to analyze, to understand kind of why certain kind of dissipation is good, and how you still achieve fast rates when you have this dissipation in there. Yeah, dissipation is, it's not just trying to get rid of the energy, it's trying to get rid of the right amounts of energy at the right time. And far away from the optimum and nearby the optimum are different regimes. You want to, you don't want to dissipate very much at the beginning, you want to dissipate a lot near the end, and that's got to be done in a controlled way.
Thank you. And maybe we have time for the last question, and it's about the last part of your talk, the zero-sum game. You propose a local symplectic surgery, if I remember correctly. And I was wondering whether it's possible to further extend the algorithms to handle, say, general-sum game, where you have maybe some net structures like variational stability. Or
yeah, no, that paper already talks about general-sum games. So there is, yes, the extension is possible. But there are lots of other issues that come up. First of all, I do want to say that I'm not that interested in Nash equilibria. It's kind of the classical Stackelberg equilibria. So I think these are much more interesting for trying to bring microeconomic ideas together with the statistics. And so I've got other papers on that. But just to say that, yes, you can, the symplectic flows here are very definitely relevant to multiplayer and non-zero-sum games.
Okay, maybe following up that question, I was wondering, so there are some negative results regarding the Stackelberg equilibrium, saying that in some problems it is empty hard to achieve a Stackelberg equilibrium. So I was wondering whether there are some ways to make the algorithm work for those problems, or there's a general recipe for achieving Stackelberg equilibrium.
Yeah, no, I'm aware of those results, and I'm not knowledgeable enough really about kind of how strong they are and how you can try to get around them. I mean, it's basically I think a lot of this gonna have to do with local methods. So just like we did with kind of gradient descent, we started to explore local methods. We gave up on any kind of global optimality in the non-convex setting. Here we may have non-convex concave or non-convex non-concave, and then we're going to be looking at local methods, and trying to analyze that in a neighborhood, but then hoping that it'll actually do a little bit better than just the find the nearest equilibrium. So that's, to me, if you're a young student looking for some problems to work on, game theoretic, both coalitional and competitive and cooperative games, and especially bringing in the statistics there, that we don't know the shape of this function. We're trying to estimate parameters as we're doing this optimization towards a satisfactory trade-off between multiple players. That's kind of, if von Neumann was alive today, or David Blackwell or whatever, I really believe this is where they putting a lot of their attention. Classical microeconomics game theory, you knew all the preferences. You knew the table on which the game was formed. And the differential version, you knew the function. And that's just not the case if we're statisticians. So how can I discover the shape of the function and also try to kind of win the game? There's certainly some papers on it, but far less than in any other field I know about. Many opportunities there.
Thank you. That's very helpful, and thank you again for giving the very nice talk. And we are very honored to have you. And
oh, it's my pleasure. It's a very real honor to participate in this series, and I see lots of names of people, some of which I recognize here. It's kind of fun. with Zoom to be able to, get to learn your audience a little bit more. And so I hope to run onto many of you in the future, and hopes to see you working on problems like this. Thank you.
Thank you. And also thanks everyone for joining. We are looking forward to seeing you guys next week.